A time is coming when all that exists will cease to be. We will explore the Big Freeze, the most widely accepted scientific theory for the universe's ultimate fate, a future devoid of light, heat, and any possibility of change. Trillions of years from now, only faint shadows of what once existed will persist, and this impending cosmic silence has profound implications for us as well.
The Big Freeze, also referred to as the Big Chill, or the heat death of the universe, offers a sobering vision. It describes a cosmos in a state of endless expansion, driving galaxies apart until they are no longer visible to one another. Understanding this concept is critical, because it is far more than an intellectual exercise. It provides a glimpse into our distant future, and influences how you might consider the potential for life across the cosmos. By attempting to solve this mystery, we engage with secrets that reside at the very core of existence. You should know that the universe began as an unimaginably hot and dense point, a sort of primordial egg from which everything emerged. This point expanded over time, giving rise to the cosmos you inhabit today. However, the Big Freeze theory posits that this expansion will not end in a dramatic reversal, but will instead lead to a more subtle, yet equally final outcome. As the expansion continues unabated, stars and galaxies will drift ever farther from each other, pulled into an increasingly cold and dark void. The principal force behind this scenario is dark energy, an enigmatic influence that constitutes approximately 70% of the universe. This force is the engine powering the cosmic expansion. To help you visualize this, think of the universe as a balloon being inflated. As more air enters, every point on its surface moves farther away from every other point. Dark energy is driving a similar process in our cosmos, but it is causing the rate of expansion to accelerate over time. So what does this accelerated expansion mean for us? Temperature is another vital component of this cosmic narrative. While you may associate cold with a familiar physical sensation, the cold of the universe is far more extreme, with an average temperature of about -270 degrees Celsius. As the universe stretches, this temperature is expected to drop even lower, eventually converting all of existence into a vast, frozen wasteland. It forces you to imagine a universe where life as you know it would be entirely impossible. As stars deplete their nuclear fuel, they will inevitably begin to die, transitioning into white dwarfs before ultimately fading into cold, dark, stellar remnants. Each star that flickers out is one more step toward an eternal abyss. The surviving galaxies will continue to drift apart, becoming isolated islands in a vast ocean of emptiness. The familiar, star-filled night sky that you see today will eventually lose all of its magnificent splendor. The cosmic microwave background radiation, which is the afterglow of the Big Bang, serves as a crucial piece of evidence in this story. This faint radiation, an echo of the universe's fiery birth, offers clues about its current state and confirms its ongoing trend toward cold and darkness. By analyzing it, scientists can peer deep into the past and, from there, project the likely future of the cosmos. As the universe cools to a point where energy dissipates completely and matter becomes inert, other cosmic objects will dictate what happens next. Black holes, those perplexing cosmic entities, will continue to shape the future, with some merging to form even more gigantic black holes that will alter the very fabric of space-time. Dark matter, the invisible scaffolding of the universe, will also play a critical part in determining how the cosmos evolves in this final cooling phase. Entropy,
A concept tied to the progressive loss of usable energy will ultimately become the defining principle of the universe's fate. As the cosmos expands and cools, its entropy will steadily increase, culminating in a state of perfect equilibrium where absolutely nothing can happen. While this end is unimaginably distant, it prompts you to ask profound questions about the purpose of life in a cosmos that is destined to fade.
The consequences for life, as we understand it, are almost beyond comprehension, and the likelihood of life emerging elsewhere becomes increasingly remote in an ever-chilling universe. This raises a fundamental question. Could any form of life possibly adapt to such extreme, energy-deprived conditions? The answer might completely redefine your understanding of what life is. There are alternative theories about the universe's future, such as the Big Crunch, a scenario of collapse, or the Big Rip, a scenario of everything being torn apart, which offer different and often more violent endings. However, the Big Freeze proposes a much quieter, though no less definitive, destiny. Considering these different possibilities encourages you to reflect on what they imply for your understanding of time and space. Scientists also employ computer simulations as a fascinating tool to model the distant future. Through these complex models, you can visualize how the Big Freeze might unfold, which gives a more tangible form to a highly abstract idea. These simulations are invaluable, not just for researchers, but also for allowing everyone to contemplate the ultimate fate of the cosmos. As your comprehension of the Big Freeze deepens, it becomes essential to contemplate its philosophical weight. What does it signify for you, as a conscious being, to exist in a universe that is inexorably cooling and darkening? The knowledge that everything you see and know will eventually vanish raises fundamental questions about your place in the universe and the meaning behind your existence. In this context, the search for new sources of energy emerges as a central theme for any civilization with long-term aspirations. If the universe is indeed cooling, you have to wonder how humanity could possibly adapt to these changes and discover new methods to survive and flourish. The technologies that allow us to investigate these cosmic phenomena will be indispensable, leaving you with the ultimate question. Can our intellect and creativity defy the fading light of the universe? The discipline of astronomy itself will be transformed in this expanding cosmos. Our comprehension of the universe will be severely tested as fewer and fewer stars and galaxies remain visible. Popular culture has also engaged with the Big Freeze through science fiction, shaping your perception of what this future might be like. It compels you to ask if you are truly prepared for a cold, dark universe. Reflecting on the Big Freeze ultimately leads you to a place of profound introspection about your own humanity and your position within the immense and transient fabric of the cosmos. Throughout human history, the immense stage of the cosmos has sparked our imagination and drive to explore. But have you ever considered what it actually means for the universe to be expanding? A simple analogy is to picture a balloon being inflated. As it grows, every point on its surface gets farther from all the others. Our universe operates on a similar principle, with galaxies continuously drifting away from each other over vast stretches of time. This revolutionary understanding, which reshaped our view of reality, originated in the early 20th century with the work of astronomer Edwin Hubble. In 1929, he confirmed that galaxies are indeed receding from us. The future implication of this is profound. Eventually, many galaxies will move so far away that their light can no longer reach us, rendering them invisible. Imagine being in a room where your friends are all walking away, until only the ones nearest to you remain in sight, prompting the unsettling question of whether we are destined for solitude in a dispersing cosmos. What makes this cosmic expansion even more astonishing is that it's accelerating. The universe isn't just getting bigger, it's doing so at an ever-increasing rate. You might wonder how such a massive and apparently stable system can push outward with such force. The explanation points to a mysterious influence called dark energy, which is believed to be the engine behind this acceleration. It's akin to being in a car that speeds up even when you're hitting the brakes, a baffling phenomenon that presents countless questions about dark energy's true nature and its ultimate impact on the universe's destiny. This ongoing expansion is intimately linked to the entire history of the cosmos. If you trace this process backward, you arrive at a point when the universe was incredibly hot and dense, a chaotic soup of pure energy in its first moments. As it expanded, it also cooled, which permitted the formation of particles, atoms, and later, the vast structures of stars and galaxies we see today. This cosmic journey from a fiery past to an expanding present naturally leads us to ask, will this expansion just go on forever? As the universal expansion persists, a gradual cooling process unfolds, as the ambient temperature of space is not fixed, but is constantly dropping. Far into the future, stars will inevitably burn through their fuel and extinguish, leaving darkness in their place. Can you imagine a night sky completely devoid of stars? This could be the ultimate fate of our cosmos, a frigid, black expanse where the light of stars no longer breaks the emptiness. While the notion of a cooling universe might seem unsettling, it represents a natural, albeit final, phase of its life cycle. When stars die, they become remnants like white dwarfs and black holes, and the material they once contained scatters across space. Radiant, bustling galaxies will grow ever more distant and dim as they recede from one another. We are already witnessing the initial effects of this phenomenon. Galaxies that were observable a century ago have moved significantly farther away, their light growing fainter. Projections indicate that within a few billion years, most galaxies will be beyond our observational reach, effectively severing our connection to the wider cosmos. A key piece of this story is the cosmic microwave background radiation, which is essentially the residual heat or afterglow from the Big Bang itself. This faint radiation permeates all of space and serves as powerful proof of the universe's hot, dense origins. As the cosmos expands, this background radiation continues to cool down, acting as a direct measure of the universe's ongoing transformation toward a colder state. Its very existence and evolution help us understand our specific moment in cosmic history. Looking further into this cold future, you find that black holes will have a critical part to play. As the most extreme objects in the cosmos, they will outlast stars, continuing to gather matter, and potentially becoming the final, massive vestiges of structure in an otherwise empty void. Simultaneously, the enigmatic substance known as dark matter, which constitutes the bulk of the universe's mass, will also shape this destiny. The gravitational pull of this invisible material governs galactic evolution, and understanding how it behaves during unending expansion is vital to predicting the universe's ultimate fate. Underpinning this entire scenario is the concept of entropy, which is a fundamental measure of disorder that is always increasing over time. This principle is captured by the second law of thermodynamics, which dictates that energy naturally spreads out and becomes less concentrated, and thus less useful. This relentless march toward disorganization is what leads directly to the Big Freeze, a final state of maximum entropy where the universe reaches a uniform, cold equilibrium with no available energy to fuel any process, raising serious questions about the long-term prospects for life. This brings us to a compelling question about the fate of life in such a cold, dark future. If the universe continues its journey toward absolute zero, is it possible for any form of life, as we understand it, to endure in that kind of environment? This challenge compels you to contemplate the very definition of life and its fundamental relationship with the cosmos. It forces us to wonder if evolution could produce beings adapted to these extremes, or if all life is ultimately destined to disappear into a frozen eternity. While contemplating this frigid outcome, you should keep in mind that other hypotheses for the universe's ultimate fate exist. The Big Crunch theory, for instance, postulates that cosmic expansion might eventually halt and reverse into a universe collapsing contraction. Another idea, the Big Rip, suggests the accelerated expansion could become so powerful that it violently shreds all matter, from galaxies down to individual atoms. Scientists are still actively working to figure out which of these possibilities is most consistent with our observations. To better grasp these long-term possibilities, scientists use powerful simulations to model the universe's future and visualize what a big freeze might entail over billions of years. These models help us understand the cosmic timeline and our place within it. Ultimately, thinking about the big freeze leads to deep philosophical reflections. It forces you to consider what it means to be human in a cosmos that is gradually growing colder and darker, prompting a search for meaning that goes beyond science and touches upon the core of our existence. Contemplating the universe's ultimate destiny truly makes you reflect on what it means to be human and the possibilities that await us. Our quest for answers about the cosmos and our role within it is an unending journey, where every new discovery brings us a little closer to solving the enigma of the big freeze. Dark energy stands as one of the most profound mysteries in all of cosmology. To understand what it is, try to picture yourself in a pitch-black room where you feel a current of air pushing you, even though you can't see what's causing it. This experience of being moved by an unseen force is very similar to the effect of dark energy, which, while invisible, has undeniable and critical consequences for the universe's future. When astronomers first started charting the expansion of the universe, they found that it wasn't just getting bigger. It was doing so at an ever-increasing rate. This observation was so counterintuitive it baffled many scientists, who wondered why the universe was speeding up when gravity should have been slowing it down. The answer seems to lie with dark energy, a mysterious force that appears to be driving the cosmos toward a state of infinite expansion. Dark energy is believed to constitute roughly 73% of the universe's entire makeup. But how can something we can neither observe nor comprehend exert such a massive influence? For a simple analogy, think about a balloon. The air you blow into it makes it expand from within. And in a comparable way, dark energy is causing the fabric of the universe itself to stretch, pushing everything apart. Although it might sound like something out of science fiction, the supporting evidence is compelling. Observations of distant supernovae, coupled with data from the cosmic microwave background, have offered vital clues about this perplexing energy's characteristics. Still, the fundamental question remains: what exactly is dark energy? Is it an inherent quality of space itself? Or could it be an entirely different phenomenon we have yet to identify? To better grasp its impact, let's use a more familiar scenario. When you press the accelerator in a car, you feel a force pushing you back into your seat. You can imagine the universe as that vehicle, and dark energy as the pedal driving its acceleration. As the cosmos expands, dark energy ensures this expansion gets faster and faster, flinging everything further away from everything else. So what does this accelerating expansion imply for the future of the cosmos? As this process continues, galaxies will recede from one another until those we can observe today eventually disappear beyond our cosmic horizon into the blackness. This outcome, known as the Big Freeze,
is a direct result of dark energy's relentless push, leaving one to wonder what will remain when the stars in our sky are nothing but a distant memory. The influence of dark energy extends beyond just the expansion itself. It dictates how the universe will ultimately behave. If this force remains constant, the universe is destined to expand forever. However, if its properties were to change over time, we could be headed for a completely different fate, one where the cosmos might even start to contract back in on itself. This raises a critical question. Is dark energy a permanent, unchanging feature of the universe, or could it evolve? Letting our imaginations wander, we could envision dark energy as a cosmic magician directing the show. What if this magician decides to alter the performance, allowing galaxies to pull back together or, for a grand finale, making the expansion accelerate even more dramatically? This uncertainty is precisely what makes the study of dark energy so captivating. Scientists around the world are dedicated to unraveling this puzzle. They are using increasingly powerful telescopes and making ever more precise observations in their search for clues that might reveal the true nature of dark energy. Despite these monumental efforts, it continues to be one of the greatest challenges in modern physics, and discovering the key to understanding it could revolutionize everything we know about cosmology. Part of this investigation involves developing sophisticated theories and models, with some scientists proposing that dark energy is a type of vacuum energy, while others speculate it could be something far more exotic. As our scientific understanding advances, we must ask ourselves whether we are getting any closer to solving this mystery, or if some aspects of the universe will always remain beyond our grasp. From a philosophical standpoint, dark energy forces us to reconsider our perception of the universe and our significance within it. As humanity continues its search for answers, we are met with profound questions about our own existence and the ultimate destiny of the cosmos. What does it truly mean to inhabit a universe that is fundamentally shaped by a force we can neither see nor touch? As you explore these concepts, it's worth remembering that while dark energy is a perplexing force, the very act of studying it speaks volumes about our innate curiosity and our deep-seated need to comprehend the universe. So, when you look up at the stars and ponder what other secrets they hold, know that this very search for answers is a timeless part of the human adventure. Have you ever considered what the average temperature of the universe might be? The question seems simple enough, but the reality is shockingly cold. Across the vast emptiness of space, the temperature averages about 2.7 degrees Kelvin, which is equivalent to minus 270 degrees Celsius. To give you some context, that is colder than any location on Earth, including the most frigid parts of Antarctica. This temperature is more than just a random number. It's a crucial indicator of the path we are on. Think of the universe as a colossal refrigerator, where everything is in a constant state of flux. The brilliant stars we observe are like tiny temporary light bulbs, and as they eventually burn out, a pervasive darkness will take over. The frigid temperature of space points directly to our ultimate destiny, the Big Freeze, a future where most stars have died, and the universe has become a desolate, cold expanse. As the universe continues to expand, this average temperature plays a critical role. The expansion not only pushes galaxies away from each other, but also governs how heat is distributed across space. With galaxies moving ever farther apart, the radiation they release gets stretched out and progressively cools, contributing to this slow but steady descent into a cold, dark eternity. You can think of the phenomenon called redshift, much like the Doppler effect, where an ambulance siren's pitch drops as it speeds away from you. However, in this cosmic analogy, it is light itself that stretches
cools, and ultimately fades into the immense void. The temperature of the universe is intrinsically linked to the energy of its constituent particles. Here on Earth, warmth is the result of countless atoms colliding within our dense atmosphere. But in the near-perfect vacuum of space, particles are so widely dispersed that they rarely encounter one another, creating an environment of profound cold and highlighting the staggering emptiness of the cosmos.
The universe's falling temperature signals more than just an intensifying cold. It also foretells a descent into pervasive darkness. As stars exhaust their fuel and galaxies continue their relentless expansion away from each other, the cosmos will become progressively dimmer. Imagine you are in a vast auditorium where the stage lights slowly fade, while the closest objects stay in view for a while. Everything in the distance is steadily swallowed by shadow, which is precisely the future our universe faces, as its light sources vanish into a cold, black canvas. This universal cooling isn't merely an abstract scientific curiosity. It carries deep consequences for existence itself. Should this trend persist, the cosmos will inevitably reach a point where the environment becomes too hostile to support life in any form you might recognize. Consider for a moment what a universe devoid of life would be: an immeasurable realm of frigid stillness, where the only thing left of creation are faint imprints of a vibrant past. Researchers have determined that as the universe cools, the birth of new stars will eventually cease, compounding the effect of existing stars dying out. This inevitable decline in stellar formation will transform the cosmos into a barren landscape, populated only by stellar corpses and vast stretches of nothingness. In this far future, the last glimmers of light will emanate from faint white dwarfs and the energetic phenomena around black holes, the final echoes of a once brilliant cosmos. You should know that this cosmic chill is not uniform. Pockets of relative warmth persist throughout the universe. In massive galaxy clusters, for instance, the intense concentration of gravity generates significant heat, creating temporary refuges from the encroaching cold. Nevertheless, as cosmic expansion continues unabated, these thermal oases are also doomed to cool, ultimately surrendering to the universe's inescapable journey toward an icy end. The temperature of space is also a critical tool that allows scientists to probe the universe's history. Using advanced telescopes and instruments, they analyze the cosmic microwave background, often called relic radiation, which is the faint thermal residue from the Big Bang that permeates all of space. This ancient light acts as a cosmic fossil, providing a snapshot of the universe's temperature long ago, and enabling us to reconstruct its evolution over billions of years. There is an inexorable link between the decreasing temperature of the cosmos and the theoretical end state known as the Big Freeze. As the universe grows colder, the fundamental ability of matter to coalesce into intricate structures, such as galaxies and solar systems, diminishes significantly. Eventually, the cosmic environment is projected to become so profoundly extreme that the conditions necessary for life as you understand it will be completely extinguished. Contemplating the universe's thermal fate ultimately leads you to ponder your own place within this grand narrative. If the entire cosmos is journeying toward a cold, dark conclusion, what does this imply about humanity's purpose? It raises the question of whether we are simply a momentary flicker of consciousness in an immense, indifferent ocean of cold. This perspective serves as a powerful reminder of just how fleeting and valuable our existence is here in our current, brilliantly lit pocket of the universe. When you gaze at the night sky, have you ever questioned the longevity of those distant, twinkling lights? Stars, the colossal gas furnaces that light up our cosmos,
have incredible life cycles, but every one of them is destined to eventually be extinguished. Examining the process of their death provides a clearer picture of the cold, dark future that the universe is headed toward.
Stars come into being within nebulae, which are vast, dense clouds of gas and dust where gravity slowly pulls matter together. Once a protostar's core ignites, fusing hydrogen into helium, it transforms into a radiant engine of energy that can shine for billions of years. The truly compelling and unsettling part of their story begins when this primary fuel source is exhausted. For a star similar in size to our own Sun, the depletion of hydrogen triggers the fusion of helium, causing its core to heat up and its outer layers to swell dramatically, turning it into a red giant capable of consuming its inner planets. After this climactic phase, once the helium is also gone, the star does not detonate in a fiery explosion. Instead, it collapses into a white dwarf, an incredibly hot and dense remnant that shines with leftover heat before gradually cooling over eons, like a fading ember in the cosmic night. You might wonder about the larger implications of this process. As countless stars conclude their lives and become white dwarfs, the universe itself undergoes a profound transformation. The total output of light and energy that once bathed the cosmos begins to dwindle significantly. Each extinguished star contributes to a darker and colder universe, meaning stellar death is not just an individual event, but a key driver of the cosmos's large-scale cooling. In contrast, stars of much greater mass are destined for a far more violent demise. Upon depleting their nuclear fuel, they collapse and then detonate in a supernova, a cataclysmic explosion bright enough to outshine entire galaxies. The aftermath of such an event leaves behind either a neutron star or a black hole. Yet even these formidable cosmic objects are not eternal, and are predicted to eventually dissipate into the encroaching void. So, what is the ultimate outcome when star formation grinds to a halt? Try to picture a universe where the vast majority of celestial lights have been extinguished. Galaxies that once shimmered with the brilliance of billions of suns will be reduced to mere phantoms of their past glory. This cold and dark cosmos will be a profoundly desolate expanse, with countless frozen and derelict planets orbiting the fading embers of their long-dead stars. You may ask what becomes of the material from these expired stars. Their remnants are dispersed throughout space, seeding the interstellar medium with heavier elements. In theory, this enriched material could provide the building blocks for new generations of stars. However, in a relentlessly cooling and expanding universe, the conditions required for this cosmic recycling to occur will become exceedingly rare, slowing the process to a near standstill. The idea that the cycle of stellar life continues even in death offers only brief solace against the enveloping darkness that looms on the horizon. The universe's temperature is set to decline steadily, and in this grim future, planets and moons that were once warm will become frozen realms. Water will solidify into ice, and life as you know it will disappear, prompting the question of whether any hope persists in other cosmic corners. Although extremophile life forms might endure in the most inhospitable environments, they will be mere exceptions in a universe that is growing ever more hostile, a place where cold and darkness will ultimately reign. As we look toward this icy future, it is compelling to consider how humanity, if it manages to survive, might handle the reality of a perpetually cooling cosmos. We would be compelled to seek out entirely new sources of energy and heat in a universe that is continually moving away from us. But could our species truly adjust to an existence where warmth and light are just faint, distant memories? The end of a star is not just a singular event. It's a critical part of the cosmic narrative that is guiding us toward the big freeze. Each dying star is a stark reminder that everything in the universe operates in a cycle, and that even the most brilliant lights will one day be extinguished. With every star that transitions into a white dwarf, the cosmos sinks deeper into a state of cold and darkness, a fate that, while incredibly distant, provides a unique viewpoint on life, time, and the boundless nature of the universe. Ultimately, the stellar life cycle teaches you that even in death, there is both beauty and meaning. Every dying star imparts a legacy, a testament to the fact that anything that shines has a finite existence. So, as you contemplate the future, it is vital to remember that while the universe may be cooling, there will always be stories to tell about the stars that once illuminated our path.
Galaxies can be thought of as islands in a vast cosmic ocean, and as the universe expands, these islands drift progressively farther apart. This raises a profound question. What happens when the space between them becomes so enormous that we can no longer see them? The concept that galaxies are separating and gradually becoming invisible is a fascinating idea that invites you to contemplate the future of the cosmos. When you look up at the night sky, you can observe thousands of stars and innumerable galaxies. But this is only a tiny glimpse of what is actually out there. Have you ever wondered just how many galaxies truly exist? Astronomers estimate the universe holds more than 2 trillion of them. Yet, as the universe expands, these galaxies are speeding away from one another, propelled by the mysterious dark energy we spoke of earlier. This expansion is not a gentle drift. It is accelerating, which means galaxies are separating from each other at an ever-increasing pace. You can picture this like dots on a balloon's surface. As you inflate it, the dots move away from each other. This is how the universe functions, with the expansion of space carrying galaxies away like those dots. Over time, many of these galaxies will become so remote that their light will never be able to reach us. This poses a troubling question. Are you currently living in the golden age of cosmic observation? And what will occur when entire galaxies become nothing more than faint memories? Over billions of years, the sky will start to change in a dramatic fashion. Some of the galaxies you can see clearly today will slowly fade, much like an old memory being erased over time. Nearby galaxies, such as Andromeda, will remain visible for a while, but eventually they too will drift away, leaving the universe to seem like an immense void where stars are scarce and darkness dominates. Over time, many of these galaxies will become so remote that their light will never be able to reach us. This poses a troubling question. Are you currently living in the golden age of cosmic observation? And what will occur when entire galaxies become nothing more than faint memories? Over billions of years, the sky will start to change in a dramatic fashion. Some of the galaxies you can see clearly today will slowly fade, much like an old memory being erased over time. Nearby galaxies, such as Andromeda, will remain visible for a while, but eventually they too will drift away, leaving the universe to seem like an immense void where stars are scarce and darkness dominates. Over time, many of these galaxies will become so remote that their light will never be able to reach us. This poses a troubling question. Are you currently living in the golden age of cosmic observation? And what will occur when entire galaxies become nothing more than faint memories? Over billions of years, the sky will start to change in a dramatic fashion. Some of the galaxies you can see clearly today will slowly fade, much like an old memory being erased over time. Nearby galaxies, such as Andromeda, will remain visible for a while, but eventually they too will drift away, leaving the universe to seem like an immense void where stars are scarce and darkness dominates.
The growing separation between galaxies also changes how they interact with one another. In the past, galaxies frequently collided and merged, giving rise to some of the largest structures in the universe. But as they move apart, these interactions will become increasingly uncommon. Imagine a circle of friends who, over the years, all moved to different cities. Although they once gathered regularly, they will eventually see each other less and less. The same phenomenon is happening with galaxies. They are becoming lost in the limitless expanse of space. The light traveling from these rapidly departing galaxies will also be affected. As a galaxy recedes, its light shifts toward the red end of the spectrum, a process known as redshift. This effect is comparable to the sound of an object moving away from you. As the source gets farther away, the sound it makes becomes fainter and lower in pitch. In the case of galaxies, while you can still see them now, their light will eventually become so dim and stretched that it will fade completely into the cosmic background. Is there anything that can be done before this inescapable separation takes place? The answer remains uncertain, but scientists are continually exploring new frontiers. It is possible that in the future, we might create technologies that enable us to travel vast distances and find new worlds. Nevertheless, the fact remains that the universe's expansion is leading us to a place where even the most sophisticated technologies might be insufficient to bridge the gap to distant galaxies. The cosmic loneliness that awaits is a profound reflection on our position in the universe, where once bright companions will become distant shadows, and our perception of distance itself will become a barrier. Questions about the future of galaxies bring us to a fascinating dilemma. If the universe evolves into a place where most other galaxies have disappeared from view, how will this impact our search for extraterrestrial life? The prospects of discovering new habitable worlds will diminish as galaxies recede from our grasp. The search for life may well become a journey into the unknown, where loneliness is the defining characteristic. Despite this, as the universe darkens, scientists will continue to observe and learn, gathering knowledge for as long as they can. Scientists employ powerful telescopes and sophisticated technologies to observe the cosmos, even as it relentlessly expands. Every new finding acts as a beacon in the vast darkness, affirming that despite the ever-increasing voids between galaxies, our capacity to investigate and comprehend the universe remains. This cosmic trajectory also has profound implications for our culture and history, as the myths and narratives we weave about the stars are central to our collective identity. In a universe growing progressively colder and more desolate, humanity's focus may turn inward, compelling us to find significance not in galactic communion, but within the confines of our own existence. The destiny of galaxies within this expanding cosmos is a stark reflection of both our vulnerability and our innate curiosity. While the big freeze might ultimately isolate us in a lonely expanse, our ability to imagine, explore, and reason will continue to fuel the quest for answers. So when you look at the night sky, consider that even as the galaxies recede from one another, we are united by a powerful, enduring force. Our ceaseless search for knowledge and purpose in a universe that never loses its wonder and mystery. The cosmic microwave background, often called relic radiation, is the faint thermal afterglow that permeates the entire universe. It stands as one of the most compelling cosmic puzzles, offering insights into the past, present, and ultimate future of everything. To truly grasp its significance for the Big Freeze theory, we need to journey back to the moments just after the Big Bang, when the universe was an unimaginably hot and dense plasma. In that primordial era, light and matter were inextricably bound together in a thick, opaque fog, preventing photons from traveling freely. As the universe expanded and cooled, matter began to coalesce into distinct structures, finally allowing light to escape and embark on its journey across the cosmos. This ancient light is precisely what we now detect as the cosmic microwave background, which means that when you observe it, you are witnessing a direct snapshot of the universe in its infancy. The cosmic microwave background serves as a faint echo of the Big Bang, providing a clear signal of the universe's earliest conditions. Its direct link to the Big Freeze theory is revealed through its temperature, which currently measures an average of approximately 2.7 Kelvin, just a sliver above absolute zero. This persistent cooling is irrefutable evidence that the universe is not only expanding, but also losing heat, a process that aligns perfectly with the predictions of a final, frozen state. Through meticulous observation of this relic radiation, scientists have determined that it is almost perfectly uniform, blanketing the cosmos in a smooth, consistent glow. To understand its importance, picture a perfectly calm ocean stretching to every horizon. Its uniformity would imply a common origin and a shared history. In the same way, the evenness of the cosmic microwave background indicates that the early universe was remarkably homogeneous, reinforcing the Big Bang as the singular, foundational event that sculpted all of reality. Yet, the narrative of this relic radiation has another crucial chapter involving what are known as anisotropies, minuscule temperature variations within this otherwise uniform field. These tiny fluctuations, like imperceptible ripples on that calm ocean, were the gravitational seeds essential for the formation of all cosmic structures. Each slight variance in temperature marked a point where matter would eventually gather, giving rise to the galaxies, clusters, and superclusters that populate the universe today. Looking toward the far future, as cosmic expansion continues unabated, the cosmic microwave background itself will stretch and cool further. The brilliant light from the dawn of time will eventually fade into a barely detectable, ghostly whisper. In this distant epoch, the radiation will become a cold, dark canvas, perfectly mirroring the final, desolate state of the universe as envisioned in the Big Freeze scenario. As this ancient echo of creation dissipates, a profound question arises for any civilization that might exist in the distant future. With every galaxy having receded beyond the cosmic horizon, and this primordial signal having faded to nothing, would it even be possible to piece together the history of the universe? Future inhabitants of the cosmos might gaze into a sky of absolute emptiness, utterly unaware of the vibrant, dynamic past that once was. The fading of this radiation holds deep implications for humanity and our search for meaning, forcing us to consider what our existence would signify if this tangible link to our cosmic origins vanished. Perhaps facing a progressively colder and darker universe would make our search for life elsewhere not just a scientific goal, but an existential imperative. At its core, the cosmic microwave background reminds us that we are part of a history far more ancient and grand than we can fully imagine. It is truly remarkable that this radiation not only illuminates the universe's past, but also provides a forecast of its ultimate fate. As the cosmos evolves, so too must our scientific understanding. It acts as a fundamental pillar for our models of cosmic structure, and every observation is like looking through a time telescope, connecting us directly to creation. The potential loss of this tool in the distant future forces us to ask how our cosmic perspective would be irrevocably altered. Ultimately, the cosmic microwave background serves as a constant reminder of the universe's perpetual state of change, and as we advance, our comprehension of the cosmos will have to adapt alongside it. The story of this relic radiation is therefore inseparable from the story of humanity's quest to understand the unknown.
It is a journey that pushes us to comprehend the cold, dark, and silent destiny that may await us all.
Among the most compelling and enigmatic objects in the cosmos are black holes. You can picture a region of space with a gravitational pull so immense that even light cannot break free, which captures the fundamental nature of a black hole. But what process leads to their creation, and what is their ultimate significance for the destiny of the universe? The search for these answers leads us on a remarkable voyage into the deepest secrets of space.
The story of a black hole starts with a star of immense size. After depleting its reserves of nuclear fuel, the star's core implodes under the force of its own gravity, giving rise to what we identify as a black hole. This event is so powerful, it could be likened to a celestial firework. Yet instead of lighting up the cosmos, it leaves an abyss of darkness, a point where all matter is crushed into a singularity, a place where our current understanding of physics seems to completely break down.
Once they come into being, what becomes of these cosmic giants? They are capable of growing ever larger and more dominant by drawing in and consuming matter. You can think of them as galactic vacuum cleaners, ingesting anything that ventures too close, from interstellar gas and dust to entire stars. This activity not only transforms their immediate vicinity, but also carries significant consequences for the universe on a much grander scale.
So, how does this fit into the theory of the Big Freeze? The influence of black holes unfolds like an intricate cosmic ballet. As they expand and proliferate, they play a part in the overall cooling of the universe. Far into the future, after the last stars have extinguished and galaxies have drifted far apart, black holes will persist as the final centers of activity in an otherwise silent and still cosmos.
However, even within this cold and desolate future, black holes themselves will start to vanish. You might wonder how something with such incredible mass could possibly disappear. The answer lies in the concept known as Hawking radiation, a theory proposing that black holes are not eternally stable. They can slowly release minute amounts of radiation, causing them to lose mass over eons, much like a campfire that slowly fades to embers until it is completely gone.
When these gravitational titans have finally evaporated and entropy reigns supreme, what will the universe look like? The absence of black holes will result in a cosmos that is even colder and more desolate. Galaxies will be separated by such vast distances that they will become practically invisible to one another, transforming the universe into an immense expanse of solitude and profound silence.
Yet, this is more than just a tale of cosmic decay. The mere existence of black holes prompts us to ask deep questions about the fabric of space-time itself. The way black holes interact with surrounding matter demonstrates that the universe is in a state of constant flux. When two of them merge, they unleash a tremendous burst of energy as gravitational waves, sending ripples through space-time and offering us valuable clues about the universe's structure and its ongoing evolution. The insights we can gain from these mergers within the context of the Big Freeze may be unexpected. While black holes appear to signify the death of stars, they also serve as a reminder that the universe is never truly static. Regardless of how cold and dark the cosmos becomes, there will always be dynamic processes at play that defy our current comprehension, with each black hole acting as a bastion of complexity in a cooling universe.
As we delve into their function, it is also crucial to examine their possible relationship with dark matter. Although we are unable to see dark matter directly, its presence is inferred from its influence on the formation of cosmic structures. It is conceivable that black holes are connected to this elusive substance, and understanding this link could provide a more complete picture of the universe as a whole. Contemplating the far future of the cosmos, one can't help but ask how black holes will shape our perspective on life in the universe. In a future where stars and galaxies have faded away, their existence introduces profound questions about life's potential elsewhere. Could these objects perhaps shelter some unimaginable form of existence? Or are they simply the final resting places for everything that once shone brightly? The impact of black holes on the cosmos is a deeply thought-provoking topic. From their birth and growth to their ultimate demise, these cosmic phenomena underscore the dynamic essence of the universe. As we head toward a future defined by cold and darkness, black holes stand as enduring symbols of the mysteries that still lie beyond our grasp, forcing us to confront the ultimate question. What is the meaning of existence in a universe that is steadily growing colder and darker? Dark matter represents one of the most significant puzzles in our universe, and its presence opens up fascinating inquiries into the structure and evolution of all that surrounds us. Even though we can neither see nor touch it, this substance is thought to constitute roughly 25% of the total mass of the cosmos. The evidence for its existence comes from carefully observing the behavior of galaxies, which allows us to infer the presence of this hidden material.
Imagine you are observing a lively party, where you can see people dancing enthusiastically, but you cannot hear the music that inspires their movements. This is a useful analogy for how we detect dark matter. Although we lack any direct observation, its gravitational effects are unmistakable. Astronomers have discovered that galaxies spin far more rapidly than their visible matter alone should permit. Based on the stars and gas we can see, these massive structures ought to tear themselves apart, but they remain intact, suggesting an unseen gravitational force is holding them together. So, what is this dark matter really made of? The name is somewhat misleading, as it is not composed of matter in any familiar sense, and its true composition remains unknown. Scientists have proposed that it might be formed from undiscovered particles that do not interact with light, rendering them completely invisible to our instruments. Among the leading hypotheses is the theory of WIMPs, which stands for weakly interacting massive particles. These hypothetical particles could be the source of the additional gravity needed to keep galaxies from flying apart. But you might be asking why understanding dark matter is so critical when discussing the Big Freeze. The answer is straightforward. Without it, the cosmos would be an entirely unrecognizable place. Dark matter is not only essential for forming large-scale structures like galaxies and their clusters, but it also fundamentally affects the expansion of the universe itself. If dark matter were absent, the gravitational pull of all the visible matter combined would be insufficient to keep galaxies from flying apart. You can think of the universe as an immense cosmic tapestry. The ordinary matter we see would be the vibrant threads, while dark matter would act as the underlying framework giving it structure. Without that crucial support, the threads would simply unravel, and the universe would lack the grand design we observe today. Now, let's consider what this means for the distant future. As cosmic expansion continues, a trend supported by current observations, dark matter will have a decisive say in how that process unfolds. It's fascinating to contemplate how it might shape the universe's ultimate destiny. Should the expansion continue to accelerate, dark matter could be the very thing that preserves a degree of coherence among galaxies, even as the space between them grows ever wider. As the universe progressively cools and expands, the influence of dark matter may grow even more pronounced, yet we must ask ourselves if we truly grasp its nature. The honest answer is no. Our journey to understand it has only just begun. Scientists are actively trying to detect dark matter particles directly in deep underground laboratories and with powerful particle accelerators. But thus far, every attempt has come up empty. This raises a profound question. Will we ever directly observe dark matter, or are we simply using the wrong methods to look for it? The search for dark matter is often compared to seeking a single needle in a haystack the size of the cosmos. We are certain it's out there, but its fundamental properties remain an elusive mystery. Furthermore, this invisible substance has deep implications for how structures formed in the early universe. In its absence, galaxies would have developed in a completely different manner, and many of the cosmic phenomena we take for granted would not exist at all. For instance, the entire process of star and planet formation could have been profoundly altered. A universe devoid of dark matter might have been a significantly more desolate reality, with a much sparser scattering of stars lighting up the night sky. When you reflect on the role of dark matter, it's intriguing to realize its impact extends beyond galactic structure and into the very foundations of our physical laws. It has forced scientists to reevaluate their core theories and explore new models to explain the forces shaping our reality. This type of research, while incredibly complex, serves as a powerful source of inspiration and intellectual curiosity. Dark matter forces us to challenge our perception of the cosmos and to acknowledge that what remains unseen may be just as vital as what is visible. As our exploration of space continues, the enigma of dark matter will undoubtedly remain a central topic of intense interest in scientific debate, suggesting that our ultimate comprehension of the universe hinges more on what we cannot see than what we can. Ultimately, the answers to these questions have the potential to completely reshape our understanding of existence itself. Dark matter is a foundational element of our universe that remains largely beyond our comprehension, with an influence that spans all of cosmic time, shaping both the present-day structure of the cosmos and its distant future. The significance of this unseen material echoes through every corner of the universe, and as we push the boundaries of knowledge, we may one day finally unlock the secrets it holds. Now, are you prepared to delve deeper? Entropy is another captivating concept that lies at the heart of physics and cosmology. But what exactly is it? And why is it so crucial for understanding the universe's fate? In simple terms, you can consider entropy a measure of the disorder within a system. Imagine walking into a perfectly organized room, but as time passes and items are used and misplaced, that room becomes increasingly chaotic. This growth in disorder is analogous to how entropy functions across the entire universe. In a cosmic context, entropy describes the distribution of energy, which has a natural tendency to move toward a state of greater disarray. As time progresses, the universe evolves toward maximum disorder, which means energy becomes more spread out and consequently less available for useful work. This relentless increase in entropy is an unavoidable process that is directly tied to the theorized end state known as the Big Freeze. So, why should this concept matter to you? As entropy climbs, energy becomes less concentrated and, as a result, less capable of performing work, which has profound consequences for the evolution of the cosmos. As stars exhaust their fuel and galaxies continue to drift apart, the universe will inevitably become a colder, darker, and emptier place. In such a state, the conditions required for life as we understand it will no longer be sustainable. Can you even conceive of a universe devoid of light, warmth, and usable energy? To help you grasp this, let's use a simple, everyday illustration. Think of a hot cup of coffee left in a cool room. Over time, the thermal energy from the coffee will dissipate into the surrounding air, and the drink will cool down. This is a perfect example of energy transitioning from a concentrated form to a more dispersed one. The very same principle is at play throughout the universe, but on an unimaginable scale, as stars, which are immense concentrations of energy, eventually burn out and cool, adding to the total entropy. Now, what becomes of the energy that is left? As the Big Freeze takes hold over eons,
the quantity of useful energy will plummet dramatically. This implies that, at some point in the far future, even the fundamental chemical reactions necessary for life will come to a halt. It's like an engine that, having depleted its fuel supply, inevitably sputters and dies. The same fate applies to life and the very processes that create new stars and solar systems.
Entropy also directly influences the physical structure of the universe. As systems evolve and descend into a more disordered state, the complex arrangements we observe today, like majestic galaxies and star clusters, will eventually disintegrate. In this sense, you can picture entropy as a cosmic force that relentlessly pulls everything back toward a state of simplicity and chaos. What does this mean for us?
On a philosophical level, this journey into the distant future encourages you to contemplate the transient nature of our existence and the very definition of life. As we delve into the universe's ultimate fate, it's vital to recognize that entropy is far from an abstract idea. Its effects are visible in every part of the cosmos, as energy dissipates, stars extinguish, and a profound cold gradually asserts its dominance.
Entropy functions like a cosmic timepiece, marking the moments until the universe achieves thermal equilibrium, a state where all energy is uniformly spread out, eliminating any temperature variations. When this occurs, the cosmos will enter a final state of so-called heat death. Yet, even in this forecast, you might wonder if there is room for optimism. While entropy points toward a frigid and dark destiny, it concurrently prompts us to ask compelling questions about new kinds of life or civilizations that might arise and adapt to such severe conditions.
Throughout cosmic history, life has consistently demonstrated an incredible capacity for survival in the most inhospitable settings. It's plausible that even within a perpetually expanding and cooling universe, life will forge new pathways to not only endure, but also to flourish. As the era known as the Big Freeze begins, the cosmos will likely be a realm of remote galaxies, dim white dwarfs, and solitary black holes. A scene that serves as a powerful testament to our own brief moment in the immense expanse of space and time.
Ultimately, entropy reinforces the principle that change is the only true constant in the universe. So, while the long-term outlook might appear desolate, every living moment and each star that illuminates the night sky stands as a celebration of the profound beauty of creation. Reflecting on entropy's role in the universe's destiny brings you face to face with a deep question. What is the real meaning of existing in a cosmos that is irreversibly dimming and growing colder? Perhaps the Big Freeze shouldn't be viewed as a conclusion, but rather as the next chapter in the cosmic saga, reminding us that every instant is invaluable and that life is an extraordinary gift.
As the universe continues its expansion and cooling, you are confronted with intriguing questions about the future of life on other worlds. This cosmic evolution directly challenges the survival prospects for any living beings. The forms of life familiar to us rely on a delicate balance of specific conditions. But what happens when those circumstances are radically altered? A planet like Earth, which has enjoyed a stable climate for billions of years, might see its temperatures plummet, disrupting the very foundation upon which its biosphere was built. Imagine a world where liquid water, the cornerstone of life as we know it, becomes permanently frozen. The survival strategies for creatures dependent on it would have to be completely reinvented. As stars exhaust their fuel, the energy and light they emit will dwindle, jeopardizing any organisms that depend on them. Photosynthesis, the engine of life on Earth, would be compromised, causing the entire food chain to unravel. In such a cold, dark universe, survival would transform into a challenge of epic proportions. However, not all organisms are created equal, and on our own planet, some have mastered survival in the most extreme places, from deep freeze temperatures to oxygen-deprived environments. But could even these resilient life forms adapt to the scale of a universally cooling cosmos? Biology possesses an astonishing flexibility, yet the Big Freeze compels us to question its ultimate limits and to redefine our very understanding of what it means to be alive.
The search for habitable exoplanets, worlds orbiting other stars, becomes a race against time. As the universe ages, the number of planets capable of sustaining liquid water and stable temperatures will likely decrease. This cosmic reality also forces you to confront profound philosophical dilemmas. If we accept that the universe is destined to cool and that life as we know it will cease, what does that imply for the significance of our own existence? Is life merely a fleeting spark in a constantly transforming cosmos? The thought that everything you know could eventually be consumed by cold and darkness deepens the appreciation for every moment. Scientists are actively investigating extreme environments for life, like the subsurface oceans suspected to exist on the icy moons of Jupiter and Saturn. While these hidden seas may harbor microbial life, they too will eventually succumb to the pervasive cold. The hope of discovering life in unexpected corners of the cosmos may slowly diminish, leaving behind a silent, frozen void. This scenario also makes you reflect on the future of intelligent species. If humanity manages to endure in a progressively colder universe, what will our civilization look like? We might be compelled to migrate to new star systems or pioneer technologies that enable us to thrive in conditions we currently consider unsurvivable. These concepts, once the domain of science fiction, could become the astonishing reality of a distant future. As the ambient temperature of the universe drops, the adaptive pressures on all living things will intensify, perhaps forcing evolution down entirely new paths. It is conceivable that we could witness the rise of life forms that do not rely on heat or light, but instead are perfectly suited to a cold and dark existence. The true diversity of life across the cosmos might be far greater than anything you can currently imagine. In this evolving universe, life may become an increasingly rare and precious marvel, a small beacon of warmth against the vast backdrop of cosmic cold. This perspective raises urgent questions for us. How much time remains? And are we preparing for the consequences of a universe that is steadily darkening? Finding the answers is essential to grasping our role within the cosmos. And yet, as you explore these immense questions, new sources of hope emerge. Scientific knowledge is always advancing, bringing with it the possibility that humanity can find solutions to adapt. Fields like renewable energy, interstellar travel, and biotechnology represent potential avenues for our survival in a cooling world. Life in the universe, though facing an eventual chilling threat, continues to be a profound source of wonder and exploration. Speculating on our survival in a frozen future forces us to confront life's incredible resilience and our own unyielding quest for understanding. It raises the question of whether we are prepared to meet such a cold destiny, or if we will be trapped in the eternal twilight of a big freeze. How you answer this may very well define humanity's role in the immense and enigmatic cosmos. The ultimate fate of the universe is a fascinating puzzle, prompting you to consider numerous potential outcomes. While the Big Freeze is a leading contender, it naturally leads to another question. Are there other possibilities for the cosmos? Indeed, alternative theories move beyond endless cooling, presenting different futures like the Big Crunch and the Big Rip, each holding its own distinct mysteries. The Big Crunch proposes a future where the universe's expansion eventually halts and reverses into a cosmic contraction.
You can visualize this as a balloon that, after being fully inflated, begins to lose air, shrinking until all of existence collapses back into a single point. This theory speculates that gravity could one day overpower cosmic expansion, drawing every galaxy back together in a final, dramatic implosion.
Imagine a reality where, instead of a cold, desolate universe, you are faced with a compressed cosmos, where everything known is crushed into a singularity. This concept of cosmic collapse is deeply unsettling, yet it prompts us to think about a cyclical universe. If the Big Crunch is a real possibility, it could imply a perpetual cycle of expansion and contraction, raising profound questions about what this means for time and whether anything could endure such a cosmic rebirth. Contrasting this is the Big Rip, a scenario that presents a completely different and far more violent end. In this model, dark energy, the mysterious force accelerating the universe's expansion, grows so overwhelmingly powerful that it tears apart the very fabric of reality. You can think of it as a thread stretched beyond its limit until it violently snaps, obliterating everything from galaxies and stars down to the atoms themselves, leaving behind nothing but an absolute void. This outcome forces us to confront fundamental questions about the nature of dark energy itself. If this force is capable of shredding the cosmos, what other unseen powers might be operating in the dark? The Big Rip scenario casts doubt not only on the universe's future, but also on our very grasp of the fundamental laws of physics, making you question the stability of everything you know. These theories of the Big Crunch and the Big Rip are not just captivating intellectual exercises, they powerfully underscore the fragility of our existence. While the Big Freeze suggests a slow, quiet fade into darkness, the Big Crunch offers a dramatic, fiery conclusion, and the Big Rip culminates in total chaos. You are left to wonder which of these scenarios is more daunting, and which, if any, might offer some faint hope of renewal. Each of these possibilities carries profound implications for our understanding of life, consciousness, and purpose. In a universe that slowly cools to nothing, life as you know it would gradually cease. In a Big Crunch, you might witness the entire history of the cosmos play out in reverse, while the Big Rip suggests that reality itself is fundamentally unstable, challenging your perception of existence. It is truly remarkable how the Big Freeze, the Big Crunch, and the Big Rip are woven together into a complex tapestry of the universe's potential destinies. Every theory presents not just a different end, but also a challenge for you to reconsider your own place in this vast cosmos. The future you choose to contemplate inevitably shapes your perspective on humanity's significance in a universe where the rules of time and space are not fixed. Ultimately, our curiosity about the future compels us to search for answers and to better comprehend our position in this immense universe. Science provides the instruments for exploring these grand theories, yet it simultaneously reveals the staggering depth of what we still do not know. Learning to embrace this ignorance can be liberating, allowing you to approach the great unknown with a sense of genuine wonder and awe. Isn't this part of the intrinsic beauty of the universe? In the face of overwhelming darkness and cold, the pursuit of knowledge and understanding becomes a powerful act of defiance. Exploring these alternative cosmic fates, therefore, not only deepens our grasp of the cosmos, but also invites you to reflect on your own existence in a universe defined by constant change. As you contemplate these futures, remember that each theory is a testament to the curiosity that drives us all. Have you ever stopped to appreciate the sheer complexity of the universe? Now, imagine if you could replicate everything we observe, from the grandest galaxies to the most fundamental particles, entirely within a computer. This is the incredible field of universe simulations,
a critical tool in modern cosmology that lets us gaze into the cosmic future and explore concepts like the Big Freeze.
These simulations function much like a colossal video game, where scientists construct a mathematical representation of the universe and then set it in motion. The foundation of these virtual cosmoses lies in the physical laws that govern our reality. Principles like gravity and the expansion of space are programmed into sophisticated algorithms, allowing researchers to simulate how galaxies, stars, and dark matter evolve and interact over billions of years. One of the most compelling applications of these simulations is understanding what they can reveal about the Big Freeze. By accurately modeling the ongoing expansion of the universe, scientists can run these simulations forward in time. This allows them to project how the cosmos is likely to behave in the distant future, giving you a clearer picture of what that long, cold era might actually look like. If the universe continues its current expansion, our simulations predict a future where galaxies drift so far apart that the night sky becomes devoid of starlight. In this projected reality, the cosmos transforms into a boundless, dark void. It's truly remarkable to consider that with these models, we can foresee not just the destiny of entire galaxies, but the very end of the stars themselves. Can you envision a cosmos where no stars illuminate the darkness? Our simulations allow us to witness stars depleting their fuel, collapsing into white dwarfs, and eventually cooling into even darker, inert objects. The brilliant light that once permeated space will gradually diminish, ultimately leaving behind a frozen and desolate universe.
Simulations are also indispensable for comprehending the function of dark energy in this entire process. While this mysterious force accelerating cosmic expansion is impossible to observe directly, scientists can incorporate it into their models. By doing so, they can watch how it shapes the dynamics of the universe, almost as if they were playing a cosmic game of chess, anticipating every move and its consequence.
And the inquiries don't stop there.
What is the ultimate fate of dark matter? This invisible substance, which makes up a significant portion of the universe, is another critical element in our simulations. As galaxies move away from one another, dark matter serves as the structural scaffolding of the cosmos, and these models let us investigate how it influences the destiny of galaxies and interacts with dark energy.
As our simulation capabilities improve, scientists are able to generate a variety of alternative scenarios. What would happen if the expansion were to cease, or if the universe were to start contracting upon itself? Modeling these distinct possibilities reveals a spectrum of potential futures, each telling a unique cosmic story and compelling us to reflect on the fundamental nature of time.
The extraordinary power of these simulations also extends to their capacity for education. Picture having the ability to observe the Big Freeze unfold, witnessing the universe cool and darken through a dynamic visualization. Such graphical depictions are not merely fascinating, they make highly complex ideas approachable for everyone, from students to avid science followers.
The technology powering these cosmic models has leaped forward remarkably in recent decades. Due to the advent of high-performance computing, researchers can now execute calculations that were previously inconceivable. Every simulation represents the combined effort of physicists, mathematicians, and astronomers working together to decode the universe's secrets, piecing together a giant cosmic puzzle.
Of course, the question of their precision always remains. Every scientific model operates on a set of limitations and assumptions, a fact that researchers readily acknowledge. As we gather new information about the cosmos, particularly from advanced telescopes, these simulations are constantly being refined and recalibrated, driving the cycle of discovery ever forward.
The future for universe simulations looks exceptionally bright. With the ongoing development of artificial intelligence and machine learning, we are poised to see models of even greater complexity and accuracy. Imagine a simulation where every star, galaxy, and black hole is rendered with an unprecedented level of detail. An idea that could completely reshape our understanding of cosmology. Fundamentally, simulations of the universe are far more than scientific instruments. They are our portals to the unknown. They provide us with a chance to reflect on the ultimate destiny of the cosmos and to view the Big Freeze not merely as an ending, but as a profound journey across space-time. In exploring these models, we are engaging in a deep conversation about existence, time, and our own position in this immense universe.
Reflecting on the Big Freeze inevitably leads us to question not only the fate of the cosmos, but also our own existence. What would it signify for humanity to inhabit a universe that is inexorably cooling and dimming? Contemplating this outcome makes it impossible to avoid the question: what is humanity's place in a cosmos moving toward a state of stillness and silence?
The vision of a cold, dark universe might appear disheartening, yet it also challenges us to examine our relationship with the cosmos more deeply. In such a context, the search for meaning becomes an urgent necessity, a method for confronting the reality of a distant future where everything we know may be altered. Philosophy provides the tools to process this ultimate fate, posing the profound questions about life's purpose that thinkers have debated throughout history. Entropy is a central concept in this entire discussion, referring to the universal tendency toward disorder and reminding us that all things are in a constant state of transformation. In a cooling universe, energy dissipates, and with it, potential opportunities fade away. However, one could also perceive this growing disorder as a fertile environment for the emergence of new perspectives and ideas. Entropy is a central concept in this entire discussion, referring to the universal tendency toward disorder and reminding us that all things are in a constant state of transformation. In a cooling universe, energy dissipates, and with it, potential opportunities fade away. However, one could also perceive this growing disorder as a fertile environment for the emergence of new perspectives and ideas.
Ultimately, considering the Big Freeze compels us to face our own fragility. It challenges us to find significance in a future where stars no longer illuminate the sky. The idea of a universe in perpetual change serves as a powerful reminder that while our individual lives are fleeting, every moment holds value, prompting us to consider what legacy we will leave on this vast cosmic stage. Perhaps the solution resides in the bonds we share with each other. In our quest for understanding, we unite to explore the cosmos through science, art, and philosophy, turning the search for meaning into a collective journey. This vision of a cold future also forces us to consider our duty to this planet and its preservation. What kind of legacy will we pass on to subsequent generations in a universe that is gradually cooling? And how might our stewardship of the world today shape the way we encounter what is to come? Are you truly prepared to face the solitude of a deserted cosmos? Science fiction has delved into these concepts in compelling ways, with films and books envisioning dystopian futures where humanity fights for survival in a chilling universe. These stories do more than just entertain. They urge us to contemplate our own existence. What actions would you take if confronted by the reality of the Big Freeze? And could we possibly adapt and discover new ways to live? In this light, the pursuit of new energy sources and the exploration of space assume entirely new significance. Humanity might be compelled to innovate, devising creative solutions to navigate a changing cosmos.
One can only wonder what technologies could arise from our fundamental need to survive in a cooling universe. Human curiosity is an immense driving force, one capable of pushing us far beyond our perceived limitations.
Philosophy also encourages us to examine the very essence of time. Does time progress in a straight line, or could it be cyclical? Within a universe that is both expanding and cooling, time acquires a different kind of meaning. While the thought of a desolate future might appear grim, it also serves as a potent reminder that time is an invaluable resource. How do you decide to spend it? And what narratives will you choose to tell upon this cosmic stage?
Ultimately, the concept of the Big Freeze brings us face to face with the impermanence of everything we know. The fact that life, stars, and galaxies are all transient can be profoundly liberating, reminding us that each moment holds weight and every action carries significance. Are you willing to accept uncertainty and perceive the beauty in what is fleeting? In this way, a philosophical meditation on the Big Freeze transforms into a path of self-discovery, prompting us to look inward and challenge our most fundamental beliefs.
What does it genuinely mean to be human in a universe that is losing its warmth? The answers might be as varied as the stars themselves, but the journey toward that understanding is what truly counts. We find ourselves at a critical juncture in our history. The manner in which we face the future and pursue meaning and connection will shape our course through this immense universe. As we search for answers, philosophy, science, and creativity all become intertwined, leading to the ultimate question. In the context of the Big Freeze, what story will we decide to tell about ourselves? As you gaze into the vastness of the cosmos, a singular question emerges. What will become of the energy we require for survival as the universe cools down? In a cosmos growing steadily colder and darker, the hunt for energy sources transforms into an epic challenge. This raises a critical point about humanity's capacity to thrive in an unpredictable future, since energy serves as the very bedrock of our civilization. From illuminating a room to fueling a spacecraft venturing to the universe's edge, energy is woven into every facet of our lives. However, as the universe continues to expand and the stars begin to dim, this question gains a new urgency. How will we secure the energy needed in the distant future, when the brilliant stars familiar to us are reduced to faint embers? Consider a future where we have depleted every resource on our own planet. Our sun, the principal source of our energy, is destined to swell into a red giant and later shrink into a white dwarf. What will we do then? Humanity will be forced to look outward and explore other options. One potential avenue lies with M-type stars. Though small and cool, they could sustain technologically advanced civilizations for vast periods. Another fascinating idea involves harnessing the energy of dwarf stars. While they are far dimmer than our own star, their incredibly long lifespans could be leveraged by future societies. The real question is whether we can invent the technology required to tap into these remote resources, and the solution will almost certainly depend on our ability to innovate and adapt as the human mind becomes our most crucial tool. Dark energy, the enigmatic force propelling the expansion of the universe, also holds a vital place in this puzzle. Although we cannot harness its power directly right now, comprehending its nature could unlock new possibilities. Could we one day learn to manipulate it for our own benefit? Science fiction frequently toys with the idea of re-engineering the fabric of space-time itself. Might we eventually tap into the energy of black holes or the power of cosmic strings? While these notions may sound like pure fantasy, they dare us to think beyond our current constraints. The future of energy in a cooling universe might rely on our capacity to first imagine and then engineer solutions that seem impossible today.
Although this sounds like a far-off dream, the annals of science are replete with accomplishments once deemed unattainable. Within the context of a chilling cosmos, civilizations might be compelled to transition to more sustainable energy systems that are less reliant on stellar output. Nuclear fusion, for instance, offers an alternative that emulates the very processes at the core of stars, and the dream of efficiently replicating this reaction could be the key to survival. Our current renewable energy sources on Earth can also provide a blueprint for the future. Solar, wind, and geothermal power demonstrate how we can utilize environmental resources without exhausting them. In an ever-expanding universe, we may need to shift our focus to harnessing resources from other celestial objects, such as asteroids or moons with energetic potential. Space mining could become commonplace, allowing us to harvest energy on a galactic scale, rather than depending on a few select planets. This question of energy also naturally leads us to contemplate the existence of life on other worlds. Should the Big Freeze scenario become our destiny, you have to wonder what other civilizations might be flourishing in different solar systems. It's possible some are already devising ingenious methods for surviving in a universe that is gradually cooling. By exploring other worlds, we could uncover the secrets of how different life forms have adapted to exceedingly harsh conditions. As you ponder these concepts, it's crucial to acknowledge that science is progressing at an unmatched rate, and what seems like pure fantasy today could very well be the reality we face tomorrow. The search for energy transcends a simple technical problem, evolving into a philosophical inquiry. What will it signify for our species to successfully adapt and even flourish within a cooling cosmos? This challenge isn't merely about locating power sources. It's also about discovering a sense of purpose against a backdrop of immense spatial emptiness and isolation. Our future requires us to reconsider our fundamental connection to energy and the universe itself. Because every flick of a light switch is a use of the same forces that brought the cosmos into being. The universe, in all its limitless mystery, sets a captivating stage and asks a compelling question. How can we possibly navigate and comprehend a cosmos that is steadily growing colder and darker? The pursuit of energy in a future defined by the Big Freeze is more than a scientific objective. It is a profoundly human adventure. Imagine yourself adrift in a vast ocean where every star is a glimmering wave in the night. As galaxies separate and stars extinguish, the urgency to find new sources of power becomes paramount. Our first step on this journey is to fully grasp the energy sources we currently possess and project how they will change over time. Solar power has long been a pillar of our civilization, but its reliability is finite. When our sun begins to cool and eventually collapses into a white dwarf, the solar energy we rely on will drastically decrease. The critical task will be to maximize the power we can harvest from it before its light fades for good. In a cooling universe, nuclear energy could assume a pivotal role. Picture a power station that not only employs fission, but also harnesses nuclear reactions capable of lasting far beyond the lifespan of stars, perhaps operating in the vacuum of space and fueled by resources from asteroids. While this sounds like science fiction, technological progress is steadily closing the gap to this reality. Nuclear fusion, the very process that fuels stars, presents an even more tantalizing prospect, promising a nearly infinite energy supply if we can finally master it on Earth. Of course, this quest for energy isn't just about production. It's equally about efficient storage and distribution. While modern batteries are a remarkable achievement, you should envision a future with not just high-capacity cells, but also vast, planetary-scale storage methods using technologies like flow batteries or supercapacitors. Could we stockpile enough energy to endure extended periods of cosmic darkness and extreme cold? This will be a defining challenge for generations to come. Venturing farther into space may also present unforeseen opportunities for energy acquisition. The moons of Jupiter, for instance, harbor vast liquid oceans beneath their icy crusts, hinting at the potential for life and untapped energy reserves. Establishing colonies on these celestial bodies could shift from being a mere possibility to an absolute necessity for survival. Back on Earth, renewable sources like geothermal energy will also become central to our strategy, tapping into our planet's enduring internal heat as the universe outside grows ever colder. Throughout this journey into the future, technology will be our indispensable guide. Artificial intelligence and advanced robotics will become crucial for exploring and extracting resources from hazardous environments, perhaps even spearheading our search for new energy frontiers. Yet, as we pursue these solutions, we must engage in deep ethical reflection. The search for power cannot be a reckless scramble for survival. It must be a conscious and responsible endeavor, mindful of how our actions might impact life that may exist elsewhere. Ultimately, the quest for energy in a cooling universe is an odyssey filled with immense challenges and incredible possibilities, inviting us to pioneer new frontiers and innovate on a cosmic scale. Human history is a testament to our ability to overcome and adapt. With enough ingenuity and unwavering determination, we may just discover a way to thrive in a universe that appears, at first glance, to be set against us. This future may be the grandest stage yet for the next chapter in our extraordinary story. The prospect of the Big Freeze will ultimately compel us to redefine our entire connection to the cosmos. As the final stars extinguish, the question arises: can humanity adapt and discover new ways to exist in an increasingly cold and dark universe? Our success will hinge on our capacity for innovation and our courage to venture into the vast unknown. The destiny of the cosmos is not predetermined, and our quest for new energy sources is set to become a defining chapter in this epic story. Even as the cosmos cools and grows dim, our innate curiosity and profound need to comprehend our place within it will continue to propel us forward. We are faced with a critical question. Will we be prepared to confront this ultimate challenge and harness what the universe has left to offer? The answer to this will likely shape not just our long-term survival, but the very legacy we pass on to all future generations. With every step into that future, you should remember that the hunt for energy is more than a simple necessity. It is a grand adventure that captures the very essence of what it means to be human. Contemplating the astronomy of the distant future is a truly captivating exercise, filled with possibilities and mysteries that compel us to imagine how our perception of reality will shift as the universe continues its relentless expansion and cooling. What will it be like to witness a cosmos where entire galaxies are perpetually receding from one another? Answering this requires you to consider not just the advanced technologies we might develop, but also the fundamental ways we will need to interpret the cosmic phenomena we observe. As the expansion of the universe proceeds, galaxies will drift further apart, their light fading until they become invisible to us. Picture yourself on an endless sea, where islands representing galaxies slowly recede from one another, until they eventually vanish over the horizon. This is a glimpse into the night sky of the future, an emptier space, where most of the galaxies familiar to us today will have disappeared from view, forcing the astronomers of that era to radically adjust their methods and expectations.
Currently, our powerful telescopes allow us to view distant galaxies with remarkable clarity, but this will not always be the case. Once those galaxies move so far away that their light can no longer traverse the distance to reach us, astronomy will have to pivot its focus toward the few celestial objects that remain gravitationally bound and accessible. Even the stars, our beacons in the cosmic dark, are destined for a bleak end, eventually exhausting their fuel and collapsing into faint white dwarfs. Astronomers will need to devise entirely new techniques to study these dying stellar embers, a challenge that could revolutionize our knowledge of stellar evolution. Technology will undoubtedly serve as the cornerstone of future astronomical endeavors. How will we manage to explore a universe that is simultaneously expanding and losing its energy? We can envision the development of incredibly advanced space telescopes, outfitted with sensors capable of detecting the faintest light from the most remote objects across multiple wavelengths, like infrared and radio waves. This would grant us access to cosmic phenomena that are currently beyond our grasp, opening new windows of understanding. Furthermore, the rise of artificial intelligence promises to transform how we process astronomical data. Faced with immense data sets, AI could identify subtle patterns in celestial bodies that a human observer might easily miss, potentially leading to discoveries that reshape our entire conception of the universe. Simultaneously, the search for extraterrestrial life will demand greater creativity. Astronomers will need to investigate unconventional locations, such as the icy moons of gas giants or exoplanets orbiting the remnants of dead stars. Alongside direct observation, the field of astronomy will lean more heavily on sophisticated modeling. Computer simulations will become crucial instruments for scientists, enabling them to project the behavior of stars and galaxies across billions of years within an expanding cosmos. These virtual universes will allow us to visualize the distant future and better comprehend the cosmic timeline. This immense undertaking will also necessitate unprecedented international collaboration, as sharing data and resources among the global scientific community will be essential to making any significant progress. As visual observation becomes more limited, the scientific community will intensify its search for alternative methods of perceiving the cosmos. Imagine if we could develop technologies that let us listen to the universe rather than just look at it. Fields like gravitational wave astrophysics and the search for intelligent radio transmissions could transition from the periphery to the very center of astronomical research, becoming our primary means of cosmic exploration. Ultimately, confronting the reality of the Big Freeze will force a profound philosophical introspection about our place in the universe. The sheer loneliness of an increasingly cold and dark cosmos may lead us to reflect deeply on the human condition and our unending quest for meaning. The question of what it signifies to be a conscious observer in a universe that is slowly fading away will likely grow more urgent and central to our thinking. While the Big Freeze may appear to be a daunting end, it also represents a powerful catalyst for human ingenuity and curiosity. The astronomy of the future could unveil entirely new cosmic horizons, revealing aspects of reality we cannot yet even conceive. The pursuit of knowledge is a fundamental part of our nature, and as the universe transforms, so too will our understanding of it. Therefore, the true question is not whether we can adapt, but rather how we will choose to navigate this incredible journey into the unknown. This very concept has also carved out a compelling niche in popular culture, where science and fiction frequently merge. But what kind of impact has this idea had on the stories we tell in films, books, and television series? When you examine the link between art and science, you find that the universe's cold and dark nature is not just a subject for academic debate, but also a powerful wellspring for creative expression.
A compelling illustration of this is the film Interstellar, which imagines a future where humanity must venture into space to survive. The film confronts you with a chilling question: what happens if our planet Earth can no longer sustain us? This narrative compels us to consider our own survival and the search for a new cosmic home. This very premise mirrors the core ideas of the Big Freeze theory, suggesting a future where humanity might face a similar predicament by having to find shelter in an increasingly unforgiving cosmos. In literature, books such as The Hitchhiker's Guide to the Galaxy playfully engage with the concept of a vast, cold, and empty universe. The notion of a cosmos where stars eventually burn out, forcing life to either adapt or face extinction, resonates deeply with the themes of the Big Freeze, inviting you to contemplate our existence and its fragility. Science fiction provides a medium for us to envision potential futures, whether viewed through a lens of optimism or despair. In this context, the Big Freeze transforms from a scientific hypothesis into a rich narrative backdrop, challenging you to think about our place in the cosmos and how our present-day decisions might influence our distant future. These stories ultimately lead us to fundamental questions. What is the meaning of being human in a universe that is slowly cooling? And how will we confront the immense challenges that await?
Video games also offer you a chance to engage with these ideas directly. For instance, titles like No Man's Sky allow you to traverse countless worlds, each with its unique climate and environment. Within this game, you can feel the profound solitude of space alongside its sheer magnificence. A poignant reminder that, in a future shaped by the Big Freeze, these worlds could become increasingly frigid and deserted. This raises the question of what exploration truly signifies when the very fabric of the universe is drifting apart.
The television series The Expanse also delves into themes connected to cosmic expansion and the fight for survival in a hostile setting. Set in a future where humanity has colonized the solar system, the show forces you to consider complex political, ethical, and survival dilemmas. It makes you wonder how people would grapple with the reality of a universe growing steadily colder and darker, and whether we would successfully adapt or simply be left behind in the cosmic tide. Musical compositions and entire albums have also drawn inspiration from the Big Freeze theory, with alternative rock bands often singing about the inevitable isolation that accompanies the universe's expansion. Their lyrics frequently paint pictures of dying stars and distant, receding galaxies, cultivating a melancholic atmosphere that aligns perfectly with the idea of a final cosmic winter. This makes you consider whether art is a reflection of our most profound anxieties about what lies ahead. The concept of the Big Freeze has even penetrated the world of comedy, where television shows like The Big Bang Theory use scientific principles as a framework for exploring the daily lives of its characters. Through witty dialogue and humor, complex subjects like entropy and cosmic expansion are made approachable and entertaining for a broad audience. It poses an interesting thought. Can laughter genuinely help us come to terms with the cold, dark immensity of the cosmos? Science fiction also explores the quest for new forms of life in a perpetually cooling universe, with films like Avatar contemplating the discovery of life on other worlds, even under such conditions. This prompts you to think about the incredible implications such a discovery would have for our comprehension of life itself and its ultimate place in the cosmos. At the same time, documentaries and educational programs have embraced theories about the Big Freeze, translating intricate concepts into language that is easily understood. By creating stunning visual representations of an expanding, cooling universe, these programs help the general public grasp the true scale and implications of the Big Freeze. This connection between science and popular culture is further evident in comic book universes, such as those created by Marvel,
which often feature epic struggles for survival that mirror the challenges humanity might one day face. The blending of genres allows you to question your own existence within a cosmos in constant flux.
The influence of the Big Freeze has even reached the world of fashion, where designers have crafted collections inspired by the aesthetics of outer space, employing dark palettes and cold textures to evoke the sheer vastness of the universe. Even social media memes have popularized the Big Freeze in a fun and relatable manner, using clever images and witty phrases to make you ponder the nature of existence while sharing a laugh. These small, creative expressions demonstrate that light and humor can be found even in the deepest darkness.
Ultimately, the Big Freeze transcends its scientific origins to become a mirror reflecting our collective aspirations and fears. It serves as a reminder that although the universe may be cold and immense, our capacity to dream, create, and imagine can overcome even the most daunting obstacles. As the cosmos continues its expansion and cooling, human creativity endures as a steadfast beacon of hope, illuminating our path into the great unknown and forcing us to ask what this cosmic future truly means for us.
The Big Freeze represents more than a mere astronomical theory. It's an invitation for you to contemplate your place in the universe and the destiny that awaits us. Confronting the idea of a perpetually cooling cosmos can feel daunting, prompting us to question how we can discover meaning in a future where stars extinguish and darkness prevails. In this context, the fundamental question arises: can there be any hope for us in a chilling universe? The answer may very well be found in our species' remarkable ingenuity and capacity for adaptation. Throughout our existence, humanity has shown an incredible talent for survival and even flourishing under the most hostile conditions. From the creation of the first tools to our ventures into outer space, we have consistently overcome obstacles that once appeared insurmountable. It is this same creative spirit that could guide us toward new forms of life and existence as we face the prospect of a cooling cosmos. Imagine a distant future where our planet is no longer habitable because of this universal temperature drop. What would we do?
Perhaps our survival would depend on finding new homes by venturing beyond our solar system, making the search for exoplanets in habitable zones a matter of utmost urgency. This raises the question of whether we are prepared to build colonies on other worlds, possibly on Mars or the moons orbiting Jupiter and Saturn. While the notion of interplanetary travel might seem like a distant fantasy, science is progressing at an astonishing rate. Each new discovery in space technology brings us one step closer to making off-world habitation a reality. But it also forces us to consider if we can truly adapt to such profoundly different environments. These questions about humanity's future in a cooling universe are not confined to science. They are deeply philosophical. What does it mean to be human in a cosmos that is growing cold and dark? If the life we understand today eventually vanishes, what legacy will we have created? Facing the enormity of the Big Freeze also prompts questions about our relationship with the universe itself. A deepening sense of cosmic isolation could be overwhelming, yet it might also inspire a newfound sense of community, compelling us to unite as never before. Ultimately, in a cooling universe, our interconnectedness may become our greatest asset. Finding solutions to existential problems will likely demand unprecedented international cooperation, whether in discovering new energy sources, exploring space, or preserving life on Earth. This new reality could also profoundly reshape our culture, altering the very stories we tell about ourselves and the cosmos. Perhaps our art, literature, and films will reflect this struggle for survival, turning science fiction narratives about saving humanity into our guiding myths. The search for hope in a darkening universe could very well become our most significant undertaking. Faced with the cold fate of the cosmos,
it's easy for you to feel small. But instead of giving in to despair, we can recognize that the choices we make today can shape a better future. The true challenge may not simply be to survive, but to find meaning and purpose in the face of this adversity. In the end, the Big Freeze compels us to decide how we want to be remembered, suggesting the answer lies in how we choose to live and care for one another, finding light in the encroaching darkness. Have you ever considered that as the universe expands, it simultaneously descends into a state of greater disorder? This relentless increase in entropy can be pictured as a perfectly assembled puzzle breaking apart, until only scattered pieces of its former coherence are left. In this way, the Big Freeze serves as a stark reminder that every instance of order is temporary, and that chaos is an ever-present, underlying reality.
This cosmic narrative inevitably raises questions about the fate of life as we understand it. What will become of living organisms within a universe that is perpetually cooling down? The potential for life on other worlds becomes a particularly urgent consideration, prompting us to envision advanced civilizations struggling to adapt to an increasingly inhospitable cosmos. One must wonder if they could devise methods to endure in this frigid, expanding reality. A question whose answer may depend as much on the inherent resilience of life as it does on scientific breakthroughs. The concept of the Big Freeze also introduces profound philosophical questions that echo our own human experience. What is the ultimate significance of our lives in a universe that is steadily growing larger and darker? As we grapple with our own mortality, we might find a measure of comfort in the idea that we are a component of something much larger, a brief, shining moment within the immense expanse of the cosmos. Could it be that our quest for knowledge and understanding is our most meaningful response to the infinite emptiness?
Of course, projections about the distant future can take various forms, and the Big Freeze is by no means the only narrative available to us. Human imagination is a formidable tool, empowering us to investigate alternative scenarios like the Big Crunch or the Big Rip. Each of these theories provides a fresh backdrop for speculation and contemplation. The real value of exploring these possibilities may lie in their capacity to inspire new ideas and challenge our current perceptions of the universe.
In this unfolding story, the search for new sources of energy emerges as a critical theme. Picture humanity confronting a future of endless cold, compelled to seek out novel solutions within an ever-expanding cosmos. Could technological progress hold the key to our survival in such a hostile environment? Innovation itself becomes a symbol of hope, reminding us that even in the face of immense adversity, the potential for human creativity remains.
Future astronomy will undoubtedly be a profoundly different endeavor. In a universe where stars are receding beyond our view and entire galaxies are vanishing from the night sky, astronomers will face unprecedented challenges and opportunities. Their work might transform into a kind of nostalgic art, where they function as archaeologists of a bygone era, piecing together the history of a universe that was once vibrant and teeming with light and life. Popular culture has also drawn significant inspiration from the idea of the Big Freeze, with films, novels, and television series exploring the implications of a cold, dark cosmos. This has undeniably shaped our collective perception of science and the future. It encourages a deeper reflection on the ways art and science can intersect, generating powerful stories that help us navigate and comprehend the vast unknown. Ultimately, contemplating what the Big Freeze signifies for humanity and our position in the universe brings us to a crucial point of reflection. Can we truly discover meaning in such an uncertain future? The answer might be found in our unique capacity to adapt and our relentless drive to find answers, even in the deepest darkness. As the cosmos follows its trajectory, we, as conscious beings, possess the remarkable ability to imbue our own existence with purpose. The Big Freeze is an invitation to meditate not just on the end of a cosmic era, but on the incredible journey that has brought us to this moment. Through our questions and our reflections, we cultivate a space for hope and curiosity to flourish. In a cooling universe, perhaps it is the warmth generated by our inquiry that will keep the flame of exploration burning bright.